Conceptually, we should know that smaller atoms generally form stronger bonds. Okay. An example of that would be fluorine. Okay. Versus, let's do iodine. Now we know from the periodic table that iodine is a larger atom. And fluorine is a smaller atom. Okay? And if you look at these on table 7.2, I do hope this is in here. I normally don't use this. Okay, so iodine is 150. The units are kilojoules per mole. Okay, and that's the amount of energy you would have to break 1 mole of iodine. Fluorine, it's, oh gosh, is it alphabetical? How is this thing even arranged? It's really random. Okay, so fluorine is 160 kilojoules per mole. Okay, so fluorine is a stronger bond. It requires more energy to break that. Okay, so that's point number 1. Point number 2 is that all else being equal, triple bonds are stronger than double bonds. Than single bonds. Now it's kind of hard to find an element that forms all of these types, but let's just use acetylene, ethylene, and ethane. So here are the Lewis structures of these organic molecules comprised of hydrogen and carbon. And using table 7.2, we can see that a carbon-carbon triple bond is, so that's that central one in all of these molecules, 837 kilojoules per mole. And let me hunt around 611 kilojoules per mole, and the CC is 345, okay? All right, so if you have a friend falling off a cliff, you could hold on to them with one hand. That's a certain amount of energy, saving their lives. If you hold on to them with 2 hands, that's more energy. And I'm sorry, I don't have an analogy for a human with 3 hands, okay? So that's the basics of that. So shorter bonds are stronger bonds, and we're going to use these now to figure out the heats of reaction, right? So let's talk about the heat of reaction. All right. So we have this thing called delta H, or delta H reaction. I like to put a little thing there so you know what it's talking about. And the formula that you want to use here is equal to the sum of the enthalpies of bonds broken minus the enthalpies of bonds formed. And I don't know why, but I'm just going to use the book here since we're doing this in the book. So bonds broken minus bonds formed. I normally use the letter H, but your book uses letter D, and I don't want to have a bunch of questions about that. D represents the bond energy. Bond And I'm going to put a little note for myself so I don't go crazy. Dissociation energy. Okay, so that's where D comes from. It comes from dissociation, but it's basically the bond energy. All right. Now, as a general comment here, if you have a reaction like this, okay, bonds are going to be broken in the starting materials. Bonds are going to be formed over here in the products. So some students, they like to trivialize things and they ask me, so it's backwards, right? And I say, well, I'm sorry, forget about that. I was thinking about something else. So the bonds that are going to be broken are here and the bonds that are formed are here. Pretend like you're making a new Lego creation and you got to break apart your other ones first to make a new thing. So you're going to break apart your old Lego cars and trucks and stuff like that to make two new Lego trains or planes or whatever, okay? So those of you who played with Legos in your youth know what I'm talking about. So let's do some examples here to, kind of start out slow. So what you need to do is draw the Lewis structure of all reactants products. Okay. You want to use table 2 to get the D's, or the bond dissociation energies. Okay. And then you want to use the formula, right? It's going to be broken minus formed. Okay. When you break bonds, it's endothermic. It takes energy. When you form bonds, it's exothermic. It forms energy or releases energy. I should probably say releases energy. That's a better term. So that's why there's that negative sign there. The negative sign takes care of the release part, okay? So let's do this for ammonia. Hydrogen and nitrogen combine to form ammonia. Now I need to balance this chemical equation, so I'll put a 2 there and a 3 here, okay? Step 1, draw Lewis structures. Hydrogen looks like that. Hydrogen looks like that. Hydrogen looks like that. Why am I drawing 3? Because there's a 3 there. I want to draw 3 of the little pictures. I need 3 of those Lego pieces. What does nitrogen look like? I just need 1 of those. Nitrogen, we've drawn this before in the class, is a triple bond. And ammonia we've drawn looks like, well, there's 2 of them. Ammonia is a central nitrogen, 3 hydrogens, a central nitrogen, 3 hydrogens. Okay. Now, when you use Sable 7.2 to get energies, you're just getting the energy of one single type of bond. So an HH bond is worth 436 kilojoules per mole. A nitrogen triple nitrogen is worth 946 kilojoules per mole. And the NH bond is 390. I should mention that in the book you see HN, that's the same as that's the same as NH. Okay, so same thing. You're just looking for HN or NH. All right. Now this is where you ignore the coefficients, like these circled 3 and 2 in this balanced chemical equation. This is where you need to count bonds. So in step 3, we need to count bonds. All right. So the delta H for this reaction is the bonds broken. You see, we have 3 of these bonds. So we have 3 times 436. Okay. We have 1 of those bonds. 946. Okay. And then how many bonds do we have on this side? How many NH bonds do we have? I count 6. I count 6 of them, okay? So we have 6 of those types of bonds, and they're each worth 390, okay? And this is where we want to subtract, okay? Subtract that. So let me grab my calculator and get a final answer here on the screen so we can, you know, admire a number, I guess. So you can use parentheses if you like. I would recommend doing that. 436, 946. Okay, and then minus parentheses 6 times 390, parenthesis, and I get minus 86. Okay. So without having to do any thermochemistry experiments or measuring temperature and all of that, theoretically we could just do the math and calculate it. All right. So that's how you calculate delta H for this chemical reaction. We would say this is exothermic, and overall it releases heat. Let's do another one. Let's do the combustion of methane. This is not balanced, so let me balance it quickly so we have something to work off of. 1 C, 4 H's, 4 O's, 2 and 2, 4 O's. Okay, so here we go. We have a starting point, and the question is, what is delta H? Okay. So step 1, we need to draw some Lewis structures. Okay, I'm not going to spend the time to do dot-to-dot structures. I'm just going to draw them all out. Okay. Now, when you draw your Lewis structures, if you have a coefficient of 2, that means 2 molecules. That means 2 pictures. Okay. And so we have to draw those in there. And we have 2 water molecules, don't we? 2 water molecules means 2 of those pictures. Okay. All right, so we've got 1 CH4, 2 oxygens, 1 carbon dioxide, and 2 waters. So that right there is correctly set up. Now we use table 7.2 to find the bond strengths. So a CH is 415. And oxygen, be very careful. Use the double bond, okay? Not the OO, but the O double O. That's 498. Okay. And the CO2, we have 741. Okay. I should mention that this one molecule actually has 2 of those, right? But each one is 741. And then we have an OH bond. We have a bunch of those in this molecule. Let me see if I can find that. Okay, 464. And now we use the formula, right? Delta H is equal to the sum of the bonds broken minus formed. So it's going to be, how many of these bonds do we have? I count 4. Okay, so those are broken. How many oxygen double bonds? I see 2. And then we want to subtract all of the formed ones. Okay, so here's the broken one. We want to subtract all of the molecules that are formed, and we have a bunch of things here, right? So for the carbon dioxide molecule, we have 2 OC double bonds. So 2 times 741. Notice how they're inside of the brackets here. Okay, we also want to subtract the water, right? These bonds are forming as well. How many of these bonds do I break? I'm breaking 4 of those, right? So we're doing this pictorially. We're not using the coefficients anymore at this step. Make sure that all of this is subtracted. So on my calculator, what I like to do is I like to do the bracket stuff first. Okay, so I'm going to calculate all the broken stuff. And use your parentheses on your calculator to keep things straight. Okay. And I'm going to calculate all that in the parentheses. And again, use your parentheses there. And so we'll go ahead and, subtract these two numbers. And I get negative 682. Okay. So that's the delta H for this chemical reaction just from the bonds. Okay. Now we don't know what the states are, liquid, gas, solid, whatever. We're just counting bonds. Okay. So it's a very crude way of just figuring out based on bonds which way is more favored or not. We don't know if we're talking about liquids, solids, or gases, so really we can't correlate this with the heats of combustion straight off the bat or something like that, okay? So it's a different way of calculating the delta H, all right? Let's do one more. Sorry, it takes me a while to draw these molecules out carefully. In chemistry, we call this an addition reaction. And ethylene reacts with chlorine to give you dichloroethane. And yeah, there's a bunch of stuff going on here. So in this molecule here, we have two types of bonds. We have a CH bond, which is worth 415. And we have a C double bond, C, which we've previously talked about, is 611. Here we have a chlorine-chlorine bond, which has an energy of 243. Okay. And a CH bond over here. All of these bond energies are a positive amount because it takes that amount of energy to break it. We know we're forming it on the right side though. And this is 345. And a CCl is the third type. 330 looks like, okay? All right, so we want to calculate the delta H from that famous formula. It's all of the bonds broken minus the bonds formed. And you'll see that in this balanced chemical equation, we just have 1, 1, 1. That's not going to help us out at all here. We need to count bonds. So there's 4 CH bonds. There's 1 carbon-carbon double bond. Okay, that's the ones we're breaking. I'm presenting this a little bit more slower in this one in case people are still lost. And then we want to subtract all the bonds that are formed. If we count the CHs, we have 4 of those CHs. And we have, let's see, 1 CC. Okay. And we have 2 CCLs. Okay. We have two of those bonds. All right. Now you'll see that actually, technically, nothing happens with the CH. All right. 4 of those CH bonds break, and then you're making your Lego pieces, and you're like, oh, I just have to put those studs right back on their position where I just took them off. So we can, not use that part if you like. If you're more of an advanced student and you see that right off the bat, cool. So we'll use just the bonds that are technically breaking and forming here. So the CC is 611. Okay, that'll be easy to do. That's just one of those and nothing else. Now for the bonds being formed, we have a carbon-carbon single bond, which is 345, and 2 carbon-chlorine bonds, which are 2 times 330. Okay. Now I like to do all the stuff in the bracket first because keep things separated here. So that's 1005, and that's 611. Now we subtract these two, we get a number, and so this is negative 394. So this is another exothermic reaction. All right.